Welcome to today's Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss dedicated outdoor air systems and the impact that the supply air dew point has on space humidity levels. On today's program, we'll start by reviewing the definition of a dedicated outdoor air system. Next, using a psychrometric example, we'll demonstrate the impact that the dew point delivered by the dedicated outdoor air unit has on space humidity levels. Then we'll review the process for determining the right supply air dew point for a given application. And finally, we'll discuss various ventilation air delivery configurations and control strategies. To cover this topic today, we have Trane Application Engineers John Murphy, Eric Sturm, and Ronnie Moffitt. So John, can you start us off by reviewing the definition of a dedicated outdoor air system?
Sure. Dedicated outdoor air systems are used in a variety of building types to provide ventilation, particularly when zone-level terminal units are used for cooling and heating. Common examples include VRF, water source heat pumps, fan coils, small DX split systems, PTACs, chilled beams, or sensible cooling terminal units. As the name implies, this system uses a dedicated unit to condition all the incoming outdoor air being brought in for ventilation. Meanwhile, a terminal unit provides cooling or heating in each zone. But in our industry, terminology can sometimes be confusing. People often use the same term but have different meanings. The term dedicated outdoor air system is no exception. To avoid confusion, AHRI has included a definition in its rating standard 920 for DX dedicated outdoor air units. Now, I included the actual text in your handouts, but I'll go back to this diagram to highlight the key characteristics of this definition. First, a dedicated outdoor air unit is sized to deliver the amount of outdoor air prescribed for ventilation. Now, typically, this is just the minimum quantity of outdoor air required by the building code or AHRI standard 62.1. Second, this unit is used to dehumidify the outdoor air to satisfy the building's latent load. We're going to talk a lot about this during today's program. And third, it's used in combination with a separate, sensible cooling system. In this diagram, a terminal unit is installed in each zone to provide cooling or heating. In addition, this unit may include an exhaust air energy recovery device to precondition the outdoor air, and it may include some means to reheat this dehumidified air when desired. Now, some dedicated outdoor units use DX refrigeration, while others use chill water. Most of our discussion today applies to either case. So, using a dedicated unit to condition the outdoor air separately from recirculated air can make it easier to verify sufficient ventilation airflow is delivered to each zone. And when that outdoor air is dehumidified so it's drier than the space, it can also help prevent high space humidity levels. But many of the dedicated outdoor systems designed and installed today are not dehumidifying adequately. Let's demonstrate why.
Let's look at a typical installation. Consider an example interior conference room in an office building in Atlanta, Georgia, using a 55-degree supply of ventilation air. The conference room is 1,000 square feet and has a design occupancy of 25 people. Using the AHRI 62.1 ventilation rate procedure, the outdoor air requirement was determined to be 185 CFM. Using a whole building energy analysis software program like Trace 3D Plus, the design loads were calculated: 11,800 BTUs per hour sensible and 3,900 BTUs per hour latent. This represents a sensible heat ratio of 0.75. The desired space set points are 75 degrees dry bulb, 50% relative humidity. This equates to a dew point temperature of 55 degrees. Conditioned ventilation air is provided by a dedicated outdoor air system supplying dehumidified and cooled air at 55 degrees. The ventilation air is cooled and dried, then delivered directly into the space through supply air ductwork. A terminal system serves the entire building, so one is installed near the conference room to offset the remaining loads. Return air enters the terminal unit, is cooled and discharged back into the space. Let's look at this on a psychrometric chart. Hot outdoor air at local design conditions enters the dedicated outdoor air system and is cooled and dried to 55 degrees dew point temperature. On this chart, I'm going to call that our conditioned air, CA. Knowing the quantity of outdoor air and the conditions at which it is delivered allows us to compute the amount of space load offset by the ventilation air. Our cool, dry outdoor air offsets 4,015 BTUs of sensible load, leaving 7,785 BTUs for the terminal unit. Our terminal unit is supplying conditioned, recirculated air at 57 degrees. Knowing this and the space load allows us to compute the required supply airflow. Solving this equation yields 400 CFM. We can now compute the latent load offset by the terminal unit because we know the supply airflow, supply air humidity ratio, and return air humidity ratio. Return air enters the terminal unit at 75 degrees, 50% relative humidity. This equates to a dew point of 55 degrees and a humidity ratio of 67 grains per pound. The return air is cooled to 57 degrees by the terminal unit, and as the air approaches saturation, some latent cooling is performed. The space sensible load is now completely offset by the dedicated outdoor air system and terminal system. Looking at the latent load column, notice there are still 2,265 BTUs of latent load left. This is because the combination of dehumidification provided by the ventilation air and terminal unit are not enough to offset the entire space latent load. Let's see how this looks on a psychrometric chart. Within the space, the conditioned outdoor air and air supplied by the terminal mix, yielding a mixed supply air condition, CA plus SA. The mixed supply air heats up and gains moisture along the sensible heat ratio, 0.75, until reaching the space dry bulb temperature. This results in a new zone condition with higher humidity compared to the desired level. Due to the differences between the desired zone condition and the new condition, another psychrometric iteration is required. The dedicated outdoor air system will continue to condition the outdoor air and deliver it at 55 degrees. Return air is conditioned by the terminal unit and supplied to the conference room at 57 degrees. The two conditioned supply air streams mix, and this mixed air absorbs heat and moisture within the space along the SHR line. Since the SHR line intersected the previously calculated zone condition, we'll say this loop has now closed on the second iteration. Here are the two zone conditions with the desired space condition on the bottom and the actual psychrometrically determined condition above it. They're at the same dry bulb temperature, so the zone sensor on the wall is satisfied, but they're at different dew point temperatures. So at design, this combination of 185 CFM at 55 degrees and our 400 CFM terminal unit at 57 degrees results in a space dry bulb temperature of 75 degrees and a dew point of 57 degrees. This means the resulting space relative humidity is 54% compared to the target of 50%. Now this was at design, but what happens at part load? At part load, the outdoor air conditions are different. For this analysis, I'm going to use design dehumidification weather because the outdoor air conditions represent a peak humidity condition. On the chart, you can see the new condition is designated with DD to indicate design dehumidification weather, while the original is marked with CD to denote cooling design weather. Compared to the previous outdoor air condition, the new condition is cooler and more humid. At part load conditions, the conference room loads are different compared to design, which results in a different sensible heat ratio. At design, we were at 0.75, and at this part load condition, we're at 0.67, so there is a greater ratio of latent load compared to sensible load. And in this analysis, we're using a variable speed terminal unit to condition the conference room. So at part load, the terminal unit operates at minimum speed, which is 75% of the design fan airflow. The ventilation air is conditioned by the dedicated outdoor air system to 55 degrees. Now before we go any further, the zone level analysis required several iterations, but I'm not going to show those. Instead, we're going to just show the final closed loop for brevity. Return air enters the terminal unit and is cooled down, but not as cold as cooling design due to the reduced space load. The conditioned outdoor air and terminal supply air mix. Finally, the conditioned return outdoor air mixture heats along the SHR until reaching the space dry bulb temperature. At part load, the terminal unit delivers less air. This results in a higher zone dew point, 61 degrees. This is approximately 62% relative humidity at 75 degrees dry bulb. Now we looked at one more part load condition. This time, the sensible load is reduced even further, resulting in an SHR of 0.61. The iteration is available in your handouts. At this condition, outdoor air is still delivered at 55 degrees. Due to the reduced space sensible load, the terminal unit continues to run at part speed and cycles, resulting in a warmer supply air temperature. As we saw earlier, the space humidity increases due to the terminal unit delivering less air and at a higher humidity condition, about 63 degrees dew point or 66% relative humidity at 75 degrees. Here's a table to help summarize the psychrometric charts. In all cases, the dedicated outdoor system supply was constant, 185 CFM at 55 degrees. So the sensible load offset, 4,015 BTUs, is constant. At design, the terminal was sized for 400 CFM, and at part load, it operated at 75% of design airflow, 300 CFM. The terminal offset all of the sensible load in all cases. At part load, the terminal unit provided less dehumidified air, and the resulting space relative humidity increases.
So in this analysis, dehumidifying the outdoor air to 55 degree dew point offsets some of the space latent load, but not all of it. What's the effect of supplying even drier air to the conference room?
If we supply colder, drier air from the dedicated outdoor air system, the terminal unit will have less dehumidification duty, which results in better space humidity control. Here's the very same conference room example, but this time we're going to supply 45 degree ventilation air into the space. Space relative humidity is maintained slightly below 50% at 75 degrees. Here's an updated version of the table I showed you earlier, this time with values based upon a supply of 45 degree outdoor air. The dedicated outdoor air system offsets more sensible and latent load with a colder supply air temperature. As a result, the terminal doesn't need as much capacity or airflow to offset the remaining space loads. Finally, because the cold, dry outdoor air takes care of the latent load, space relative humidity doesn't deviate from the desired condition as much. Let's compare the 55 and 45 degree options. Now I'm showing the design and worst part load condition. That's the condition with the highest ratio of latent to sensible load, an SHR of 0.61. At part load, the 45 degree dedicated outdoor air system does a better job of maintaining space relative humidity when compared to the 55 degree option. This is because a 185 CFM supply of 45 degree air is drier than the same volume of 55 degree air, so it can offset more space latent load. Later in the program, John is going to discuss what the right temperature is, because it might not be 55 or 45 degrees.
As I mentioned earlier, a dedicated outdoor air unit might also include an exhaust air energy recovery device to precondition the outdoor air. But some system designs use just an energy recovery device for ventilation, with no other coils for cooling or heating. When this device is packaged together with fans, it's often referred to as an energy recovery ventilator, or ERV. An air-to-air energy recovery device, such as a total energy wheel or a membrane exchanger, is used to precondition the ventilation air. In the summer, sensible heat and water vapor are transferred from the hot, humid outdoor air to the cooler, drier exhaust airstream. This pre-cools and pre-dries the incoming outdoor air. In the winter, the outdoor air is preheated by transferring heat from the exhaust airstream to the incoming ventilation air.
We also analyzed an ERV to see how it performs against these dedicated outdoor air system options. A dedicated outdoor air system has a refrigeration system and controls the discharge air condition, while the ERV discharge conditions are subject to the entering air conditions and the effectiveness of the energy recovery device. Said another way, the ERV discharge air condition is not controlled, unlike the dedicated outdoor air system. At design, when the space has a 0.75 SHR, the ERV is able to deliver conditioned ventilation air at 82 degrees dry bulb, 62 degrees dew point. These conditions result in a humidity ratio higher than our desired space condition, 88 versus 67 grains per pound, respectively. This means the conditioned ventilation air is adding both sensible and latent load to the space, which must be offset through the terminal unit. The terminal unit cools the air and these streams mix. Finally, the air heats along the SHR back to room temperature. At part load, when the outdoor air conditions are very humid, the ERV delivers conditioned air at 77 degrees dry bulb and 68 degrees dew point, again adding load to the space. This air mixes with the supply air from the terminal unit, then follows the SHR to the space temperature. Like before, this isn't enough to offset the entire space latent load, and the resulting space relative humidity increases. An ERV can certainly be used to pre-cool or preheat air, but it does not control the discharge air conditions. So, the use of an ERV should be carefully considered. Perhaps the most interesting thing here is the impact on terminal unit sizing. The delivery of colder, drier supply air offsets more space load. This leaves less load for the terminal unit, which allows it to be downsized. If using an ERV, the terminal unit would be sized to offset 1.6 tons. If using a 55-degree dedicated outdoor air system, this drops to 0.9 tons. And if the air is delivered colder at 45 degrees, it drops further to 0.6 tons. Design terminal unit airflow values, the fan sizes, and corresponding power used also decreases as the dedicated outdoor air system offsets more of the space load.
Thanks, Eric. Now we understand how dew points supplied by the dedicated outdoor air unit affect space humidity levels. Next, John will step us through how to find the right dew point for each application.
The right dew point for a given application depends on the type of space and the indoor humidity level desired, as well as the type of terminal units used. Using this latent load equation, you can determine how dry the air needs to be. The result depends on the space latent load you're trying to remove, the CFM of outdoor air being delivered, and the desired humidity ratio in the space. For this discussion, I'm going to use a different space types, a K through 12 classroom. But I've also included the calculation for Eric's example conference room in your handouts. For this example classroom, the space latent load is estimated to be 4,030 BTUs per hour, and the required outdoor airflow is 350 CFM. Now, if the desired space conditions are 73 degrees dry bulb and 50% relative humidity, this equates to a humidity ratio of 60.6 grains per pound in the space. So using this equation, in order to remove the entire space latent load, this 350 CFM outdoor air needs to be dehumidified to 43.9 grains per pound. This equates to about a 45-degree dew point. Depicting this in the psych chart, the dedicated unit dehumidifies the outdoor air to 43.9 grains per pound. As we calculated, this is dry enough to offset the entire space latent load and keep the space humidity at the desired level. Of course, the result is going to differ for other space types and conditions. Again, the three variables in this equation are the space latent load, the CFM of outdoor air, and the desired space humidity ratio. Starting with the latent load. This pie chart shows the sources of latent load for example K through 12 classroom. In this case, the ventilation air accounts for almost 2/3 of the total. The remaining 1/3 is the space latent load, most of which is due to people and infiltration. These are the loads that occur within the boundaries of the conditioned space. The latent load due to ventilation affects the dehumidification capacity of the equipment, but only this space portion of the latent load is what dictates how dry the supply air must be. Of course, these loads will vary for different space types based on activity level and occupant density. Now moving on to the second variable in the latent load equation, that's the CFM of outdoor air required. In most cases, the dedicated outdoor system is sized to deliver just the minimum quantity of outdoor air required by the building code or AHRI standard 62.1. This chart shows how much the minimum ventilation rate varies from space type to space type. For spaces with higher ventilation rates, like an office or a retail store, this likely allows for a higher supply air dew point. But for spaces with lower ventilation rates, like an auditorium or a conference room, a lower dew point is likely required. We saw that in the example conference room that Eric showed earlier. Now, because of this, sometimes the system might be designed to deliver more than this minimum required ventilation in order to dehumidify adequately. Finally, the third variable in the equation is the desired space humidity ratio. In my example calculation, the desired space conditions were 73 degrees dry bulb and 50% RH. But what if the engineer or client is okay with a higher relative humidity in the space? This corresponds to a higher humidity ratio. Or what if the space set point will be 75 degrees rather than 73? Again, this will result in a higher humidity ratio. In this case, the space humidity ratio varies between 60 and 78 grains per pound, depending on the desired conditions. Now, if I go back to my K through 12 classroom example, when the desired space conditions were 73 degrees dry bulb and 50% RH, the outdoor air need to be dehumidified to about a 45 degree dew point. But with 75 degrees and 60% RH, the required supply air dew point is 53, not as dry. So you can see the range depending on the desired space conditions. And then here's the full list of space types from before, showing the same range of required dew points. Again, spaces like auditoriums or conference rooms require a lower dew point. You can see this could be very low, maybe as low as 21 degrees. But for spaces like classrooms, offices, and retail stores, the supply air dew point from the dedicated outdoor system can be more typical, ranging between 44 and 53. Again, the right dew point supplied by the dedicated outdoor unit depends on the type of space and the desired humidity level. But it can also depend on the type of terminal units being used. Some terminals are designed to provide only sensible cooling, no dehumidification. Common examples include chill beams, radiant cooling panels, and sensible cooling terminals. When these types of terminals are used, the dedicated outdoor system is the only source of dehumidification. So it has to be designed to dehumidify the outdoor air dry enough so that it maintains the dew point in the space low enough to avoid condensation on the sensible only terminals. In this case, I'm showing the space dew point limited to 55 degrees, which is below the 57 degree water temperature that's typically supplied to these types of terminal units. Now, moving on from dew point for a moment, some HVAC design engineers specify the dedicated outdoor air unit to reheat the dehumidified air to a neutral dry bulb temperature, maybe 70 degrees as an example. but this wastes energy when the zones also require cooling. To address this, AHRI Standard 90.1 now prohibits a dedicated outdoor system from reheating the dehumidified air to any warmer than 60 degrees dry bulb, whenever the majority of zones require cooling. This applies even if you're using recovered heat for reheat. This requirement was added to the 2016 version of that standard. Now in this example, I show a dedicated outdoor unit dehumidifying to 45-degree dew point. When a chill water or a refrigerant coil is used to dehumidify the outdoor air from point OA to point CC, a byproduct of that dehumidification process is sensible cooling. The dry bulb temperature of the air leaving the cooling coil at point CC is colder than the space. If this dehumidified air is then reheated to neutral from point CC to point CA, some of the sensible cooling performed by the dedicated outdoor air unit is wasted. If the zones need cooling, why not make use of the sensible cooling already done by the dedicated outdoor air unit? Otherwise, the terminal units will just need to offset more of the space sensible cooling load, increasing their energy use. Now with that said, there may be times when reheating is needed to avoid overcooling. Depending on what dew point is required, some engineers might not be comfortable with delivering the air that cold. In this chart, the outdoor air is dehumidified to a 45-degree dew point, which corresponds to a 45-degree dry bulb temperature almost. But rather than reheating all the way back up to neutral, it would be better to reheat just enough to avoid delivering colder than desired air to the spaces. In this case, I'm showing this air being reheated to only 55 degrees dry bulb. This takes advantage of the sensible cooling effect of this cold, dry air, reducing the need for recooling at the zone level terminals.
Thanks, John. For the last section of this program, Ronnie's going to discuss control of the dedicated outdoor air system along with the various air delivery configurations. Ronnie?
Air can be delivered from the dedicated outdoor air unit directly to the space through a terminal unit. When delivered through the terminal unit, the conditioned outdoor air may be ducted directly to the terminal, or the air may be ducted to a ceiling plenum or a closet where the equipment is located. In this case, the conditioned outdoor air mixes with the return air in the plenum or the closet and then supplied to the space when the terminal unit fan is running. When delivering outdoor air through the terminal unit, the system is dependent on the space cooling and heating equipment to deliver the ventilation air to the space. This means the terminal unit fan must run whenever the space is occupied, regardless of the heating or cooling requirements. This can limit the ability of the terminal equipment to cycle off or reduce fan speed at part load, unless the terminal unit can measure outdoor airflow or otherwise verify that proper ventilation is being delivered to the space. When delivered directly to the space, conditioned outdoor air is delivered independent of the zone heating or cooling terminal units. The ventilation air is delivered directly to the space via a dedicated diffuser. Zone heating and cooling equipment is not impacted by the amount of ventilation sent to the zone. This can enable zone-level demand control ventilation, which I'll discuss in a minute. But first, let's look at the operation of the dedicated outdoor air unit. Sometimes the unit can be configured to control directly based on the condition in a space, like a traditional packaged air conditioning unit. But this has many shortcomings. When the space conditions are at the desired set point, the dedicated outdoor air unit has the potential to deliver very cold air to the space in the winter or very warm and humid air in the summer. Most systems with a dedicated outdoor air unit also have terminal equipment in the space to cool or heat and control space temperature. So controlling the dedicated outdoor air unit off space temperature should be avoided, as there will be two systems fighting to meet set point. The majority of dedicated outdoor air units use discharge air control. A set amount of outdoor air is delivered at controlled discharge air temperature and discharge air dew point temperature. To meet the outdoor airflow required for the zone, the total amount of air delivered may vary, but the conditioned air will be sent at the required temperature and dew point, regardless of the airflow. These temperature and dew point set points will be determined based on the unit's operating mode. When configured with Discharge Air Control, a dedicated outdoor air unit will have up to 4 primary modes of operation: dehumidification and cooling mode, heating mode, and it may have a ventilation-only mode where outdoor air is delivered unconditioned. The mode of operation is determined based on the current outdoor conditions, both dry bulb and dew point. The dedicated outdoor air unit may or may not be equipped with exhaust air engine recovery, but this will not change these primary modes of operation. Each mode of operation will have different discharge air set points. For buildings without a building automation system, these discharge air set points are static for each mode. Or in a building with a BAS, these set points can be reset, determined by polling the zones served by the ventilation system. Let's look at these modes of operation on the psychrometric chart. In this example, the discharge dew point set point is 50 degrees. When the outdoor air dew point is higher than this set point, the unit will operate in dehumidification mode. In this mode, the outdoor air will be dehumidified to the desired dew point set point. For a package DX unit, this is usually achieved by controlling the temperature leaving the evaporator coil to 50 degrees for the example. Triggering this mode off outdoor air conditions rather than a space will prevent air with high water vapor content from being sent into the space. A cycling DX unit will have reduced latent performance and a varying supply temperature and dew point. To minimize cycling, variable speed or variable flow compressors are often used in a dedicated outdoor air unit, but even these will cycle below 20% capacity. Instead of falsely loading compressors, a DX unit will use a deadband to prevent quickly dropping in and out of this mode. This is also needed to account for the minimum turn-down capabilities of the equipment. For our example, this dehumidification mode will start whenever the outdoor air dew point is above 55, and then will not drop out of this mode until the outdoor air dew point drops below 52. For most comfort applications, this approach should be acceptable. If the unit has hot gas reheat, there will be a separate discharge dry bulb temperature set point during this mode. After the air is dehumidified, it will be reheated up to this set point. The maximum recommended set point is 60 degrees to comply with AHRI 90.1 limit that John mentioned. If there is no BAS, this set point will be constant. But if there is a BAS, it should be used to monitor the zones and reset this reheat temperature set point based on the space needs. For many buildings, no reheat is required when in dehumidification mode, so it may be best to have no reheat. If the outdoor air is hot and dry, the unit will operate in cooling mode, since dehumidification is not needed. This prevents delivering hot air into the space when the zones require cooling. In this mode, the outdoor air is cooled to the discharge cooling set point, 60 degrees in this example. Note, this mode does not start until the outdoor air dry bulb temperature is above 75 degrees. At cooler temperatures, the unit operates in ventilation-only mode, which I'll explain next. However, if you expect that some zones could require peak cooling even when it's 75 degrees outside, you will likely want this cooling mode to extend down to cooler outdoor air temperatures, like maybe 65. As I mentioned before, if a BAS is present, these values could be reset based on the needs of the spaces served. When the outdoor air is dry and the temperature is close to space conditions, the unit will operate in ventilation-only mode. The outdoor air is delivered without being cooled or heated. In this example, this occurs when the outdoor air temperature is between 50 and 75 degrees. At these conditions, the zones will most likely require part load cooling or may not need any heating or cooling. This control mode is especially beneficial for systems without a BAS. Delivering the outdoor air to the zones unconditioned will prevent simultaneously cooling and reheating or heating and recooling. The zone level thermal equipment will just cool or heat the space as needed. As I mentioned, if the zones have high internal loads, the upper limit for this mode might be set lower. When the outdoor air is cold, Below 50 degrees in this example, the unit will operate in heating mode. Here, the outdoor air is heated to the discharge heating set point, 60 degrees in this example. This heating set point is typically below or at zone temperature to ensure effective delivery of the ventilation air. If the unit includes exhaust energy recovery, the capacity of the device may need to be modulated to prevent overheating the air above this discharge heating set point. Then when it is really cold outside and the energy recovery device is at full capacity and not able to meet the set point, the primary heat, such as a heat pump, gas, or electric, is used to heat the air the rest of the way. At this time, the heating set point is often higher, like 75 degrees. As before, if a BAS is present, this heating set point may be reset based on space conditions.
These 4 different operating modes apply to almost every application and climate. But how many hours the unit will operate in each mode certainly varies by climate. Cities in the eastern United States, in the A climate regions, will have a significant number of hours in dehumidification mode. For example, here's a plot of the annual weather data for Atlanta. 46% of the hours will be spent in dehumidification mode, 9% in cooling, and 25% in heating. While for 20% of the hours, the air will be delivered unconditioned in ventilation-only mode. The further south you go, there will be more hours in dehumidification mode and fewer in heating, while in the north, there will be fewer hours in dehumidification mode with more in heating. Now contrast that to arid climate zones, region B. There will be more hours in cooling mode and not as many in dehumidification mode. In Albuquerque, for example, 33% of the hours are in cooling with only 4% in dehumidification. And for marine climate zones on the west coast, region C, there will likely be a large number of hours in ventilation-only mode. For instance, in Seattle, for 38% of the hours, the outdoor air will not need to be conditioned.
So those 4 modes are for when the building is occupied. The dedicated outdoor air unit can also be used during unoccupied hours if it is equipped with a recirculation air damper. In this case, the unit conditions 100% return air from the space and is controlled to maintain the unoccupied heating or cooling set points or a space dew point set point. Control might be based on the conditions in a representative space or based on commands from the building automation system. With terminal equipment in the space, the dedicated outdoor air unit might not be used during unoccupied hours, or it might just be used when after hours dehumidification is needed. Next, let's move on to demand control ventilation. In a dedicated outdoor air system, DCV can be implemented at the unit level or at the zone level. Unit level DCV has limited use. It can only be used effectively when the dedicated outdoor air unit serves one ventilation zone. This might be the case in a large open office area. There may be multiple terminal units and temperature control zones, but ventilation air is distributed throughout the area. In this case, the unit's fan airflow is measured and controlled directly. If there's a building automation system, it might be used to count the number of occupants or by some other means measure or predict the number of occupants in the zone. Then the BAS recalculates the ventilation requirement based on current population and sends this new ventilation set point to the dedicated outdoor air unit. Or the unit controller itself may use a CO2 sensor installed in the zone and reset the ventilation airflow set point based on this. In either case, the dedicated outdoor air unit then modulates its fan speed to maintain this desired outdoor airflow. But if the dedicated outdoor air unit serves multiple ventilation zones, then DCV should be implemented at the zone level. Each zone has a pressure-independent air valve with airflow measurement and a motorized damper. Each zone's ventilation airflow set point can be either sent by the BAS or may be calculated based on the CO2 concentration measured in the zone. The zone's controller then modulates the damper to maintain the required ventilation airflow. In this case, the dedicated outdoor air unit fan is not operating to directly maintain an airflow set point. Instead, its controller modulates the fan speed to maintain the static pressure in the ventilation duct at a set point. As the population in the zone decreases, its damper will close to reduce the ventilation airflow to that zone. Then the dedicated outdoor air unit will reduce its fan speed so as not to overpressurize the duct. As the zone population increases again, the damper will open further to increase flow and the fan speed will increase. When DCV is implemented at the zone level, the ventilation set point is determined by the zone controller and is most often based on the CO2 concentration measured in the zone. This chart depicts the control sequence with the CO2 on the x-axis and the zone ventilation airflow set point on the y-axis. At the zone design's outdoor airflow and design occupancy, a corresponding high-limit CO2 concentration is calculated per AHRI 62.1. When the measured CO2 concentration is equal to or higher than this CO2 high limit, the ventilation set point is at the design rate for the zone. Based on Eric's example conference room, the design outdoor airflow is 185 CFM, which corresponds to a CO2 concentration of 1,650 parts per million. When the measured CO2 concentration equals to or is lower than the CO2 low limit, the ventilation set point is reduced to the DCV minimum outdoor airflow. Most often, this value is the ventilation rate required for the zone area with no people present. For our example conference room, that's 60 CFM with 400 parts per million low limit. Then, when the measured CO2 concentration is between the low and high limits, the ventilation set point is calculated proportionally between these two airflow set points. For example, when only 20 people are in the conference room rather than the 25 at design occupancy, the measured CO2 will be 1,480 parts per million. This equates to the ventilation set point of 154 CFM.
So, a sensor measures the CO2 concentration in the zone and uses that to adjust the position of the damper and vary ventilation airflow being delivered. But as we saw in Eric's conference room example, the minimum ventilation required by AHRI 62.1 may not be enough to dehumidify the zone. So let's talk about how to avoid high humidity in these types of densely occupied spaces.
If the space humidity gets too high, you could use the building automation system to lower the discharge dew point set point from the dedicated outdoor air unit. This will further dehumidify the air being delivered to all the zones. Another solution is to use a humidity sensor in the zone and then increase the outdoor airflow delivered to the humid zone above the minimum required ventilation. This active humidity control sequence can be integrated with demand control ventilation. In the chart on the right, the x-axis is the zone dew point, and the y-axis is again the zone ventilation airflow set point. For this example, if the dedicated outdoor air unit supplies air at 50-degree dew point, the system would need to deliver 240 CFM of dehumidified air to our conference room in order to prevent the dew point in that space from exceeding 60 degrees at design occupancy. This becomes the maximum outdoor airflow set point for dehumidification. The distribution ductwork should then be designed to allow for this maximum airflow to this zone as needed. With active humidity control, the zone temperature and humidity sensors are used to calculate the current zone dew point, and the zone controller calculates how much ventilation airflow is needed to dehumidify the space. For example, if the dew point in the conference room is 59, this equates to 200 CFM of ventilation airflow for dehumidification. The controller then uses the larger of these two calculated airflows as the current ventilation set point. In the partial occupancy example, only 154 CFM is needed for ventilation based on CO2, but more is needed for dehumidification, so the controller will bring in 200 CFM. In this case, if the lower airflow set point was used, the space would exceed the 60-degree dew point limit.
So with active humidity control, the controller tries to minimize ventilation airflow based on the measured CO2. But by measuring humidity in the space also, it can then increase this airflow if needed for humidity control. But what about if you don't have a humidity sensor?
If there's no space humidity sensor, an alternative approach is predictive humidity control. Whenever the dedicated outdoor air unit is in dehumidification mode, the ventilation airflow set point is calculated based on a different CO2 high limit. This high limit is calculated based on the maximum outdoor airflow required for dehumidification, not the minimum ventilation rate. We calculated that 240 CFM of dehumidified air was required to dehumidify this conference room at design occupancy. This corresponds to a CO2 high limit of 1,230 parts per million. So the controller has two different CO2 high limits, and thus two different ventilation airflow set point calculations. When it's humid outside and the dedicated outdoor air unit is in dehumidification mode, this higher DCV line is used. In all other modes, the lower DCV line is used. The result is, in dehumidification mode, the ventilation set point will be higher than what's needed to meet the minimum ventilation requirements. But now the space will be under control and the dew point will be below 60 degrees.
While there are other predictive humidity control methods, this patent-pending predictive humidity control demand control ventilation is still reducing energy use when zone population is less. But the controller will bring in more ventilation airflow whenever the dedicated outdoor air unit is in dehumidification mode. This will result in lower space humidity levels. So no space humidity sensor is needed with this approach, but you might sacrifice some energy savings from DCV.
Whether unit level or zone level DCV is used, the dedicated outdoor air unit should measure airflow delivered and not let the unit airflow drop below the minimum allowed. The unit's minimum allowed airflow will vary based on equipment manufacturer, equipment type, and options installed. DX refrigeration is often the primary concern. A unit with limited stages of capacity control may have limited airflow turn down if allowed at all. However, many DX dedicated outdoor air units can be equipped with variable speed compressors and electronic control valves. With proper unit controls, this can allow DCV to turn down fan airflow to 30% of design. When designing a system with DCV, it's important to specify and verify the airflow limits. Some units may be equipped with electric or gas heat. These may have more restrictive limits than the DX refrigeration, and depending on the fan selection and system design, the fan may have a minimum allowable turn down also. When zone level air valves are used, they should have a minimum airflow set point that ensures this minimum airflow through the dedicated outdoor air unit is met. The minimum airflow allowed will vary by the DOAU equipment manufacturer, equipment type, and application. The system's minimum airflow also can be impacted by the building design. First is building pressurization. If there is a fixed exhaust requirement in the zones, the minimum ventilation airflow likely needs to be higher than the exhaust rate. Or there may be a minimum airflow to ensure proper delivery of the ventilation air through the diffusers. This can also impact the airflow turndown possible.
We hope you enjoyed this E&L program and that you found it a helpful way to learn about the design of dedicated outdoor air systems and their impact on indoor humidity. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses at trane.com/continuing education, all free and on demand. And please don't forget to fill out a survey. Let us know if this program is useful for you. Finally, ask your local host about details for the remaining Engineers Newsletter Live programs this year. Thanks for joining us today. We look forward to seeing you next time.